So hi guys, I'm Ritvik Vipra, study material science and engineering at IIT Roorkee. So today I'm going to be talking to you about Mosfet structure and working. So okay, so MOS stands for metal oxide semiconductor. Well, here you can see there's a P type. This is actually a N-Mos type field effect transistor. So FET stands for field effect transistor and MOS stands for metal oxide semiconductor. MOSFET is always a four terminal device. There's the gate, source, drain, and body. So this is actually the body, the P type silicon substrate written here. This is the source, this is the drain, and this is the gate. So this is actually a N-MOS type of device because it has a P type silicon substrate. Since it has a P type silicon substrate, it has a N type diffusion layer or dopant which forms a source electrode. Again here you have an N type diffusion layer which forms a drain electrode. This is an insulating silicon dioxide layer SiO2, here thin film, and on top of that there's a gate electrode made of titanium metal usually. So the device size is specified by the channel width and channel length, W and L. This becomes here, this becomes your length, and your width is this. Okay, so now, so there are two types of devices, NMOS and PMOS. What we saw before was an NMOS because it had a P-type silicon substrate, right? It had N-type diffusion layers, diffusion zones here, source and drain. For NMOS device, always the drain is connected to a higher voltage as the source, and here you get an induced tapering N layer. We'll get to that later. This is here the silicon dioxide insulating layer. For the PMOS type, this is exactly opposite. It's a N-type silicon substrate with P-type dopants forming the source and drain. Here forms an induced P region, P layer, which is also tapering. You can see here this is a positively charged and this is negatively charged as compared to the NMOS type, which is exactly opposite. Okay, so operating NMOS type of device at zero voltage. So the MOS structure forms a parallel plate capacitor with gate oxide layer in the middle. So this is the gate oxide layer, and this forms a parallel plate capacitor with a length L. Okay, two PN junctions are formed. Which is a one between the source and the body interface here, the other between the drain and the body interface here. So two PN junctions are formed, and they're connected as back-to-back diodes through this gate layer. The source and drain terminals are isolated by two depletion regions without conducting current. So here you can see this is the depletion region, this white region over here. The operating principles now will be introduced by using this N-channel MOSFET as an example. So positive charges accumulate in gate as a positive voltage is applied to the gate electrode. So here you can see positive voltage is applied to the gate electrode. Positive charges are accumulating here. The electric field formed inside as a result of this applied voltage forms a depletion region by pushing holes in P-type substrate away from the surface. So in the P-type substrate, the electron holes which are present near the surface are pushed away downwards to form a depletion region. This is depleted of holes or positive charge rather. So that is why it's called a depletion region. Electrons as a result start to accumulate on the substrate surface as gate voltage exceeds the threshold voltage Vt. So when the gate voltage VGS becomes greater or equal Vt, electrons start accumulating over this substrate surface here. The induced N region is thus forms a channel for current flow from drain to source. So what happens is this induced N-type channel is formed here for current for flow of current from the drain to the source. It acts as a channel. The channel is created actually by inverting the substrate from P type to N type. This is the inversion layer. So the substrate surface over here the substrate surface over here is converted or inverted actually from a p type to a n type, and thus the channel is created. The field applied, that is the voltage applied, controls the amount of charge in this channel and determines the channel conductivity. Okay, so the amount of voltage applied here determines the charge conductivity through this induced n type. So when we apply a small drain voltage, that is as the applied gate voltage becomes greater than the threshold voltage Vt, and that is used to induce the channel, this structure becomes n type enhancement, n channel enhancement type MOSFET. Okay, so this MOSFET which we are looking at is a n channel enhancement type MOSFET. So free electrons are now traveling from the source to the drain through the induced n channel due to a small VDS. So here flow of current is shown. This is conventional current, or flow of positive charges is shown. As a result, we can easily conclude that electrons are moving in the opposite direction. So if positive charges are moving from the drain to the source, electrons are moving from the source to the drain. Okay. Resulting current, which is ID, shown in the induced n channel, flows from the drain to the source opposite to the direction of the flow of negative charges. The current is proportional to the number of carriers in the induced channel. Okay, which we had seen earlier was proportional to the amount of voltage applied here. So the current ID is proportional to the amount of charge carriers in this induced n channel. The channel is controlled by an effective voltage or overdrive voltage VOV, which is given by VGS minus VT. Okay, so the electron channel, the electron charge in the channel due to the overdrive voltage is given by C ox WLOV, which is a rather technical formula. So let's not get into that. So in this region, you can see MOSFET can be approximated as a linear resistor dependent upon the applied voltage. So for VGS less or equal VT, there is no current, and for small voltages over VT, MOSFET becomes a linear resistor. Okay, inversely proportional, with the resistance inversely proportional to excess gate voltage. So we now going to be operating with increasing drain voltage. So as VDS increases, voltage along the channel increases from 0 to VDS, and the voltage between the gate and the points along the channel decreases from VGS at the source to VGS minus VDS at the drain end. So here you can see, as you increase this positive voltage applied to the drain for the N-Mos type of device, along the channel the voltage increases from 0 to VDS. Only thing is here, the voltage at this point is VDS, but here it is VGS minus VDS. Okay, so the inversion layer depends on the voltage difference between the MOS structure. Increasing VDS will result in a tapered channel, so that is why we get a tapered channel here. Current is again flowing in this way, positive current. Thing is, this is VDS, but this is VGS minus VDS. Okay, so we get a tapered region. Okay, so the resistance increases due to the tapered channel, and the ID VDS curve does not continue as a straight line anymore. So you do not have a linear resistor following the Ohm's law anymore. At the point where VDS becomes saturation voltage, that is VD sat, which is equal to VGS minus the threshold voltage, the channel is pinched off at the drain. Okay, so here the channel becomes pinched off at the drain. You may be seeing here the channel becomes pinched off at the drain here. Okay, and increasing VDS beyond this value has little effect on the channel shape, and the current saturates at this value, so it no longer depends on the applied VDS voltage. So the triode region basically is when the applied drain voltage is less than the saturation drain voltage, and the saturated region is when the applied drain voltage is greater than the saturated voltage. Here you can see the tapered channel. Okay, here you have overdrive voltage minus the VDS. Here you only have the overdrive voltage, as a result of which you get a tapered channel. Alright, this is actually a graph of the tapered channel with the values of the voltage plotted against distance x. So I'm going to go to the N-Mos IV characteristics now. So derivation of the IV relationship here, as you can see, We're going to consider infinitesimal element width dx here. Induced charge in the channel due to the MOS capacitor is minus cox into vgs minus vt minus vx. The charge is always given by capacitance into voltage. Now the equivalent resistance dr along the channel for this small infinitesimal element here is given by you're using your r is equal to rho l by a. So dx becomes the length. This hx into w becomes the area of that small infinitesimal piece, and this is the resistivity. Alright, this q nx mu n, which can be simplified and written in terms of the charge here. So now dv is equal to I into dr. You substitute, you integrate taking the appropriate limits, and you get a equation for the current actually. Alright, so you get an equation for the current, which is mu n cox w by l vgs minus vt vds minus half vd square. So the process transconductance parameter is given by this mu n cox, which is k dash n. The transconductance parameter is given by kn, which is this parameter k dash n multiplied by the aspect ratio. Aspect ratio is the width to length ratio of the channel, induced n channel. Okay, the drain current of MOSFETs as a function of the voltage is given by this. So ID as a function of VDS is given by this. You can see here is an inverted parabola. So in this triode region, you have this inverted parabola because of this relationship. In the saturated region, as we had discussed earlier, the current gets saturated and is no longer dependent upon the voltage. You get a straight line here. So this is how the IV characteristics are generated for a N-Mos type of device. Okay. So here you go. For different threshold voltages, you are getting different widths of the triode region and saturation region, and you're getting this similar curve, which is a parabola in this triode region and a straight line in the saturated region. This curve, plots the VDS equal to VGS minus VT. Okay, so this is basically the IV characteristics of an MOSFET type of device. Okay, so now we go to some interesting things about NMOS: channel length modulation, finite output resistance, the body effect, and temperature effect. If you have a good look here, you can see that let me just yeah. Channel length modulation is in fact a channel pinch off point moves slightly away from the drain as the drain voltage becomes greater than the saturation drain voltage. So you have to replace L, or the length of the channel, by the effective channel length, okay, which actually reduces with VDS. So actually L effective is equal to L minus delta L. Formula for delta L can be as you can see, can be deduced from these equations, involves some integration taking the appropriate limits. So you can basically approximate how the current varies as VDS increases. Okay, coming to finite output resistance, what this basically means is that for an early voltage type of application, you get a finite output resistance. It does not increase beyond a point, as you can see here, because this graph has been negatively extrapolated towards 1 by lambda here. Okay, so in the saturation region, it shows a finite output resistance. It has a finite, no infinite resistance can be achieved. All right. Body effect. So what happens is the body source and the body drain junctions should be reverse biased for the device to function properly, for an NMOS device to function properly. So the body of an N channel MOSFET is usually connected to the most negative voltage, all right, and the depletion region widens in BS and BD junctions and under the channel as VSB increases. So the body effect basically what it means is that the threshold voltage increases as the charge in the depletion region under the channel increases. So this variation of the threshold voltage can be given by this equation. Just let me. Okay, here you can see the body effect basically shows a variation of threshold voltage with the excess charge in the induced layer. Temperature effect, gives the what temperature effect basically says, that the threshold voltage decreases by a small amount, usually 2 millivolts for every 1 degree centigrade rise in temperature of the device. Okay, which implies that ID increases with temperature. That is what the temperature effect basically says. So thank you once again for listening to me patiently. That these are some of the basic things about the N MOSFET type of device. Similarly, we can study the P MOSFET type of device. Thank you.